I'm Aijun. I'm from University of Science and Technology of China. I'm going to talk about our work on Thompson sampling-based Monte-Carlo planning POMDPs. This is a joint work with Feng, Zongzhang, Zhang, and Xiaoping, Chen. So this is outline of this talk. So Monte-Carlo tree search is popular in these years, which is an online planning method for POMDP and MDPs. It finds the near optimal process by building a best-first search tree using Monte-Carlo samplings without explicitly knowing the underlying models in advance. So typically, MCTS runs in an iterative way. It will recursively select actions for states until a leaf node is reached, and then inserts one or more nodes to the current tree and plays a default rollout policy until certain of steps, then updates the statistics of the search path. So this is an outline of the MCTS algorithm. One advantage of MCTS is that it tends to search the most promising areas of search tree, building an asymmetric search tree. One of the fundamental problems in MCTS is a so-called exploration versus exploitation dilemma. That is, agents must not only exploit by searching the action that currently seems best, but should also keep exploring for possible higher future outcomes. This problem is usually seen as a multi-armed bandit problem, where we have a set of actions and an unknown stochastic reward function. A cumulative reward is defined as expected cumulative defined as difference of the expected difference of your actually obtained reward minus to the base reward you can have, which is actually unknown. So MAB is often solved by minimizing the cumulative reward by trading off between exploration versus exploitation. UCB1 heuristic is a famous method to deal with this kind of trading off. POMDP algorithm applies the UCB1 heuristic to select actions, which is defined in equation 2. A simple regret for MAB is defined as equation 3, which makes more sense for pure exploration problems. A recently growing understanding is that actually we should try to balance between cumulative regret and simple regret in MCTS, because it does not collect a real reward when searching the tree. However, it is still good to grow the tree more accurately by exploiting the current tree. So Thompson sampling is actually an old heuristic for MAB problem. The basic idea is to select an action based on its posterior probability of being optimal, formally expressed as equation 4. Fortunately, it can be efficiently approached by using sampling method. For this purpose, we sample a set of hidden parameters and then select the action with highest expectation given these parameters. As an example of Thompson sampling for two-armed bandit problem, we suppose we have two actions, A and B, with Bernoulli reward distributions. We do not know the actual distribution, so they have hidden parameters, PA and PB. We assume uniform prior distribution over them, so PA and PB follow the uniform distribution. And suppose we have observed a history of actions and rewards. Suppose we have applied action A and got reward 1. We then applied action B, got reward 0, and we have applied action A with another 0. Then in Bayesian settings, the posterior distribution of PA and PB could be obtained. Actually, they are beta distributions with parameters beta 22 and beta 12. Given these posterior distributions, we can sample PA and PB from, as shown in the figure. Then we select the action with the highest expectation given these sample parameters, and to finish the action selection in current step. So the motivation is that Thompson sampling theoretically achieves asymptotic optimality for MABs in terms of cumulative reward. And empirically, it has competitive and even better performance comparing with state-of-the-art in terms of both cumulative reward and simple reward. So, in terms of cumulative regrade and simple regrade. So it seems to be a very promising approach for the challenge of balancing cumulative regrade and simple regrade simultaneously in the MCTS algorithm. So the contribution of this work is complete Bayesian approach for online planning, for online Monte-Carlo planning POMDPs. We maintain the posterior reward distributions of applying action in the search tree and use Thompson sampling to guide the action selection. So this is the basic assumption of the algorithm. So let XBA be the intermediate reward of performing action in belief state B. We assume we have a finite set of k possible immediate rewards, so XBA will follow a multinomial distribution, which could we model the posterior distribution of the multinomial distribution using Dirichlet distributions, where the hyperparameters could be simply updated by using equation 5 after we have observed actual reward. And we define the random variable xsb pi as the cumulative reward of following policy pi in joint state with environment state A and agent's internal belief state B. According to the central limit theorem of Markov chains, xsb pi could be modeled as a normal distribution with unknown parameters. We model the posterior distribution of these unknown parameters using normal gamma distribution with 4 hyperparameters, which could simply be updated by using Bayesian laws as expressed in equation 6 to 9. So now we consider the cumulative reward of following policy pi in belief B. By definition, it follows a mixture of normal distributions given that we have assumed xsb pi is following normal distribution. Then we define the random variable of xba pi be the cumulative reward of applying action A in belief B and following policy pi thereafter. The distribution of xba pi could be very complex, and it's not easy to explicitly write it down, but we can simply compute the expectation of xba pi as shown in equation 12 if we know the observation function. So the question is we need to model the observation function, okay? The observation function is actually another multinomial distribution. We model the posterior distribution of the observation function as Dirichlet distribution, which could be easily updated when we have observed a real transition from belief B action A and the observation O. So given all these hyperparameters, we have maintained the posterior distributions for the cumulative reward of applying action A in the search tree. Then for each decision node associated with belief B, we use Thompson sampling to select the action. We first sample a set of parameters from these posterior distributions, and then we compute the expected reward given this parameter, which is actually can be seen as a sampled Q value. We then select the action with the highest Q value. So we named our algorithm as D2NG POMCP because we are using two kinds of Dirichlet distribution and one normal gamma distribution as the prior distribution. We conducted our experiments in log sample and Pokemon domains. We evaluate our algorithm by running the algorithm for a number of iterations for current belief, applying the best action based on the resulting action values, repeating this process until some terminating conditions, and reported the total discounted reward and the average time usage per action. So this is the experiment results in log sample and Pokemon domains. This figure is showing performance in terms of number of iterations, and the right figure is showing the performance in terms of average time per action. Actually, you can see the proposed algorithm is outperforms the POMDP algorithm, which we use as a baseline in terms of number of iterations and have competitive performance in terms of average time per action. In the log sample domains, and it actually performs much better than the POMDP algorithm in Pokemon domains, which is a very complex domain, have millions of states. So the total computation time for the algorithm is actually linear with the number of simulations, as for all the MCTS algorithms. However, our algorithm does require more computation time than POMDP due to the time-consuming operation of sampling from various distributions. However, we think that it can obtain better performance in terms of computational complexity if the simulations are expensive, actually as confirmed in the Pokemon experiments, because our algorithm is expected to have lower sample complexity because by using more information in the search tree. So to conclude, we have proposed the Bayesian MCTS algorithm. We maintain the posterior distributions of applying an action in the tree in Bayesian ways and select the action using Thompson sampling, trying to balance between cumulative regrade and simple regrade. Our basic assumptions of the distributions in principle only hold in the limit when the tree policy has converged. In future work, we try to extend these assumptions to more realistic distributions and test our algorithm on real-world applications. Yeah. Okay. Thank you.
Back on track for time. Carmel?
Yeah, thank you. So why would you like to balance, I think I'm loud enough. So why would you like to balance between cumulative regret and simple regret?
Well, actually, because in MCTS, in the search process, actually, we do not collect actual rewards, okay?
No. I'll rephrase myself. Why do we care about cumulative regret at all? Like balancing, if you balance by putting 0 here and 1 here, it's okay. But if balance sounds like we want to be good with simple regret and not bad with cumulative regret.
Yeah.
Why do you care about cumulative regret?
Okay, that's because, as I said, the search process of the MCTS algorithm does not collect real reward. What we really care about is the last action that collects a reward.
Which suggests that you want to go simple regret, right?
Yeah.
Did you try this on simple MDPs?
Yeah. Actually, we have another paper on MDPs, which is published in NIPS conference.
Will be published, or was published? Is the paper already published? The one?
Yeah, in NIPS conference.
Questions? Yeah, speaker?
Thank you.